Today we're going to start chapter 6. We're going to start in section 6.1 and we're going to do just part of it today. So we're going to talk about exponential growth and decay. So an exponential function is any function really that has an x as the exponent. We're going to look at it in the form y equals a times b raised to the x power. So only b here is being raised to the x power. The only things that we have to consider are a cannot be 0, because then that would eliminate this whole thing. B has to be positive, and it can't be 1. The reason it can't be 1 is because if I raise 1 to the first power, it's 1. If I do 1 to the second power, it's 1. If I do 1 to the third power, it's 1. So the function would not change at all if B was 1. So we are going to look at B being something else. So now we have exponential growth. So that's when B is bigger than 1. And again, A, we're only looking at really positive values of A. We call B the growth factor in an exponential growth function. The parent function, they're only looking at b to the x, so that would be a is 1, would look like this. It's rising from left to right. It goes through the point 0, 1, and 1, b. So whatever that value was that was being raised to the x power, it'll be 1, that value. Don't forget we had asymptotes. Remember, asymptotes are lines that it gets really close to but never crosses. So the x-axis is an asymptote of this graph. So the domain is all real numbers. We could put any value of x in, but it's always going to be above the x-axis, so the range is y is greater than 0. For an exponential decay function, we still have a as a positive number, but now b is between 0 and 1. Right? Still not negative, but it's between 0 and 1. And b is now called the decay factor. So in an exponential decay function, it's the decay factor. For growth, it was the growth factor. The parent function for exponential decay then falls from left to right. It still goes through the point 0, 1 and the point 1b. It's just now, because b is smaller, it's going down. All right, same domain. We could put any value of x in, and the range is still greater than 0 because the asymptote is still the x-axis. So we're going to determine whether each of these functions represents exponential growth or exponential decay and explain our reasoning. And then we're actually going to do just a quick sketch. We're not going to worry about a whole table of values. If I had a different value of a here, I would definitely be making a table of values. But since these are just based on the parent functions, we can do that. So here in my first one, y equals 5 to the x. 5 is bigger than 1, right? 5 is greater than 1, making this a growth function, right? Any b that's bigger than 1 is growth. And if I wanted to do a quick sketch, we know that it passes through 0, 1, and then it passes through 1, b, and 5 was b. So it's going to pass through the point 1, 5. And we're just going to do a quick sketch. We're not worrying so much about all the points. And that's what that graph would look like. For part B, y equals 3/8 to the x. 3/8 is less than 1, right? That's smaller than 1, bigger than 0, smaller than 1. So this is decay. And I'm still going to do a quick sketch. We know it goes through 0, 1. And then it goes through 1, b, so that's going to be 1, 3/8. That's just slightly under half. So we're going to assume it goes like right about there. And I can do my sketch like that. Okay? So you guys are going to try the next ones. We're just going to focus on determine whether each function represents exponential growth or exponential decay, and explain your reasoning. You do not have to graph any of these. Pause, and when you're ready, you can come check your answer. All right, for the first one, 0.25 was less than 1, so that was decay. For number 2, 4 is greater than 1, so that's growth. For number 3, 1.5 is greater than 1, so that's growth. And then number 4, 2/3 is less than 1, so that's decay. All right. So a lot of real life quantities increase or decrease by a fixed percent every year or every time period that they specify. So the amount y of such a quantity after 2 years can be modeled by one of these equations. So if it's exponential growth, a is our initial amount, and then it's 1 plus the percent of increase. So the r is going to be written as a decimal, and it's raised to the t power, and t stands for our time. In exponential decay, the difference is it's a minus instead of a plus. So that's why anything inside here ends up being bigger than 1 for growth because we were adding something to it. For decay, it's always less than 1 because we were taking something away. Just know that we now have something called a growth factor. 1 plus r is the growth factor. 1 minus r is the decay factor, whereas rate of growth and rate of decay are different than the growth factor and decay factor. In our first example here, in the year 2000, the population of a city was about 1.04 million. During the next 14 years, the population increased by about 2.05% each year. Determine whether this represents exponential growth or decay. So because they use the word increased, we're going to call this growth. So B, write a model representing the population y in millions t years after 2000. So it's going to be y equals, and we're always going to start with the initial amount. The starting amount here was 1.04, so that's my initial amount, 1.04. And since it's growth, it's going to be 1 plus whatever this number was as a decimal. And I know it's already written as a decimal, but this is a percentage. So if you recall, whenever you want to turn a percent into a decimal, we're going to move the decimal place over twice to the left. So if I move it over there and put a 0 in place, the decimal is really 0.0205. So if I add this amount to 1, it becomes 1.0205. I could have written it as 1 plus 0.0205, but then I have to add it together anyway. I'm not going to leave it with that plus sign there. It's not complete. Right? And it's raised to the t power. So this is the model. There's nothing we have to do to it. It has a y, it has a t. We're done. Part C, estimate the city's population in 2008. So I need to know what is the value of t in 2008. So if it's based on starting in 2000 and now it's 2008, that means we have t is 8 years. So I'm plugging in 8 right here. I'm going to write it out first, and then I'm going to show you really the steps you would do in your calculator. All right, 1.0205 to the 8th power. So we want to make sure we're raising to the power first and then multiplying. I'm going to pull up a calculator. So this is like a TI-34. Some of you may have one that's like this. We're going to do that 1.0205. And notice here it's our raised to button, raised to the 8th power. And I'm going to enter that first and get my answer. And instead of hitting clear, I'm just going to now multiply that by 1.04. So 1.22 is about our answer. So this would be about 1.22 million people, right? Now part D says using graphic calculator to estimate what year the city had a population of 1.3 million people. So I'm going to give you a code. It should already be when you downloaded this lesson to download a graphing calculator if you'd like. So you notice over here is my actual calculator, and over here's what it looks like. So I'm going to start by putting in my equation. I'm going to hit the y equals, that's up in the top left corner, and I'm going to type in that equation. So that was y equals 1.04 parentheses 1.0205 end parentheses, and I'm going to use the raised to power, so that's over here on the right hand side above division. And we're going to use a variable here. We're not going to put in the 8 because that was the last problem. We're looking for what the value will be. So if you notice next to the green alpha button, there's some variables there. I'm going to click that so we get the x. This is now my equation. It doesn't matter that I'm using x instead of t. That's fine. I could look at the graph of it, but it's probably not going to look like very much. But if I hit second graph, see how it says table? It's going to give me a table of values. And I can go up and down through this list, and I'm looking for what's the value of x when my y value is about 1.3. And the closest we get to 1.3 is right here when x is 11. So that means my answer here would be in 11 years, which would be 2011. Right? 11 years after 2000 is 2011. So you're going to go ahead and try this next one. Same idea. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. So go ahead and try these three problems, pause, and when you're ready, come back. All right, so for A, this is a growth function. For B, we have y equals 6.09 times 1.0118 raised to the t power. And in part C, we're looking for the value in 2005, so that would be t is 5, and it's about 6.46 billion. All right, here we have the value of a computer depreciates by 26.5% each year. In 2015, you bought a computer for $1,200. So we're going to determine whether this represents exponential growth or decay. So the word depreciates tells us that it's declining, it's going down. So that's why this is going to be exponential decay. For B, write a model representing the value of the computer Y in dollars t years after 2015. So this, because it's decay, is going to be minus. So we're going to have Y equals the starting amount. So Y equals 1,200. And it's going to be 1 minus 26.5% as a decimal. So move it twice, it's 0.265. So this is minus 0.265 raised to the t power. But I'm not quite done yet. I can't leave it as 1 minus 0.265. Actually, I have to do that. So my answer would actually be y equals 1,200 times 0.735 raised to the t power. And for C, estimate the value of the computer in 2020. So 2015 to 2020 is 5 years. So we're going to plug in 5 for T. So just like I showed you before on the calculator, we're going to raise this value, this decimal, to the power first. So I'm going to do 0.735 to the 5th power first, and then multiply that by the 1,200. And if we do that, we get about 257.41. This is money, so we can go to 2 decimal places, dollars. All right, the next example, The value of a car Y in thousands of dollars can be approximated by the model Y equals 31 times 0.92 to the t power, where t is the number of years since the car was new. So to determine whether this represents growth or decay, we're looking at the number in the parentheses. If it's bigger than 1, it's growth. If it's less than 1, it's decay. And 0.92 is less than 1. So this is decay. So in B, identify the annual percent increase or decrease in the value. So we're looking at how far away from 1 is 0.92. So if I do 1 minus 0.92, I get 0.08. And 0.08 as a percentage, move that over twice, is 8%. For part C, estimate the value of the car after 6 years. So we're just plugging 6 in for t here. So we have 31 times 0.92 to the to the 6. Now we have that. And when I do that, I get about 18.797. So since that was in thousands, I'm going to say 18,797. I could have said 18.8 thousand. That would have been acceptable as well. And D, use a graphing calculator to estimate when the value of the car would be 9,600. So 9,600 in terms of thousands is really 9.6 thousand. So I'm looking for when the value of the function is 9.6. So I'm going to go back to my graphing calculator. I'm going to clear out my original equation. I'm going to type in my new one. So that was 31 parentheses 0.92 to the x power. And I'm looking at the table of values. I'm looking for the closest I can get to 13. It seems to be pretty much between those two, so I'm going to say between 10 and 11 years. Right? Sometimes we're not going to have the exact, and that's okay. Do your best estimate. All right. So you guys are going to try this one. You only have to estimate the value of the car, and you're going to try it with the graphing calculator when the value of the car is 8,000. So pause, and when you're ready, come back. And I'm just now realizing I think I might have misled you on that last one as I'm writing my answer. So I'm going to go back to this. We were looking for 9.6, right? I don't know why I was looking there. 9.6 is here. 14 years. We're good. So sorry about that. We're going to change this. Boom, boom. 14 years. Because as I'm doing the next one, that's this answer, 10 to 11 years. I'm so sorry about that one. All right, almost done here. The last kind of problems we're going to talk about are radioactive isotopes. So they're telling us the amount of a radioactive isotope left after T days is given by this equation. A is the initial amount. We don't need to know the initial amount because they just want to know what percent decays each day. So what I'm going to do is I'm going to convert this to get just t as the exponent. I'm going to kind of get rid of that 28. So A times 0.5, and t over 28 is the same as 1 over 28 times t. Right? I could separate those two things. And on my calculator, I can evaluate 0.5 raised to the 1 over 28. And I'm going to go back to the regular calculator to do this. If I have 0.5 and I'm raising it to the 1 over 28, I'm going to use parentheses when I raise my power. Right? 1 divided by 28. I could have used my fraction button 1 over 28 if I wanted to. It gives me my decimal. So this is really what's inside those parentheses. And what I would want to do is 1 minus that value. So I'm going to hit second answer. and get 0.02445. So I'm going to go back here. So we know 02445. I don't remember what that number was. We'll look back again. 9755. So this is what my equation really looked like. A times 0.9755 to the t power. I did 1 minus that 0.9755. I got 0.02445. So that means it's about 2.445%. That is the percent that decays each day. So our goal was to split the t over 28 first to 1 over 28 times t, evaluate this part in our calculator, get the new decimal, and then do 1 minus that decimal to find out what the rate of change was. So you're going to try the same thing on the last one. We have that 0.5 raised to the t over 13. So separate it and find out your percentage. Pause when you're ready. Come back. Okay, so if you did 0.5 to the 1 over 13 power, we got 0.9481. And if I do 1 minus that, I get 0.0519. Turning that into a percentage, move it over twice, 5.19%. All right, and that's it for this part of 6.1.